Good evening, all of you. Is my voice clear for everyone? And the video also? Say. Thank you. So, any questions for the previous session on what we discussed about the homomorphism and isomorphism concepts? Do you have any? Yes or no? So, today's topic is permutation groups. So before going to start that, I just want to take one small problem on homomorphism. And I just want to give one definition also. Then we start with the interesting concept, that is permutation groups. Now the question is, suppose I have given two groups for you. Let me say I have taken two finite groups for you. And if you want to construct a homomorphism between these two, then how do we construct it? That was the thing, right? So here, if you take an example that you take Z4 with addition modulo 4, that is the operation, and another group as 1 minus 1 I minus I, and dot is the operation. So if you write precisely the elements in Z4, nothing but 0, 1, 2, 3 with the operation plus 4, and you are going to build a function between these two sets which is going to be a homomorphism. That was the context. And by default, we want to build an isomorphism between them. So I want a function which is 1, 1, on 2 and homomorphism as well. That is my actual intention. So did you get the context? Say. Please take a note of that. Then we discuss with that. So always one fundamental property here is we always pair the identity with identity. Now tell me, in the first set, what is the identity element there? In the first set, 0. In the second set, what is the identity element? 1. So here, you are going to define a function f from Z4 to, say, this is G, by f of 0 is equal to 1. So you have paired one element with one element. Since I am going to build an isomorphism, the interesting thing I need to observe is the two sets must have equal number of elements, because I need a bijection. Whenever there is a bijection between two sets, then obviously the elements in the both sets must be equal, the number of elements. Otherwise you cannot build a bijection, isn't it? Yes or no? That's why to have a bijection, initially I need to check how many elements are there in the first set, how many elements are there in the second set. So by comparison that, since there are equal number of elements on both sides, it is possible to construct a bijection between them. So I have paired 0 with 1. So I got one thing. So 0, 1, 2, 3 elements on this side, 1 minus 1 I minus I elements are this side, and I have paired like this. Now remaining 3 elements are there. I want to pair them with the others. Here the question comes, how to pair them? Now, since 1 is taken here, you can pair 1 with any of the things. You can pair 1 with -1, I minus I. Now the question comes, I need to pair 1 with what element? Are you getting? Yes or no? Now, before that, in the previous session, I hope we discussed one concept that the function is a 1-1 function if and only if order of A is equal to order of f of A. Could you recollect this result? What we discussed earlier? If you want to have a 1-1 function which is a homomorphism, so it means that if you want to pair an element with some other thing, both must have the same order. So here we have 1. What is the order of 1 in the domain with respect to the operation here? Here the operation is +4 if you consider. What is the order of 1 on the left hand side? It means since the operation is plus, by adding 1 how many times you will get 0? That is the question. Calculating order means. By adding 1 how many times you will get 0? It is addition modulo 4, the operation there. So order of 1 is 4. Anybody has any doubts with regard to the order of 1? Say. Any questions for anybody? Yes or no? Any doubts? Any questions? How 4 has come order of the element? Clear. Right. Now, on the right hand side, you have 3 elements, -1, I, minus I. Among the 3 elements, which element has order 4? There the operation is dot, multiplication. So while raising the powers, at the power 4, you should get identity 1. For which element order is 4? I. And minus I also has the same order. Minus I whole power 4, 1. I power 4, 1. Accepted? So, I can pair 1 with I or minus I. That is my choice. Because they have the equal order. So, here, I am going to pair 1 with the element I. Since you are dealing with the groups, homomorphism preserves the structure. So, whenever you pair an element with another element, immediately you have to pair the corresponding inverse with the corresponding inverse. So, in the domain, for the element 1, what is the inverse of 1? What is the inverse of 1 in the domain? 3, right? Because 1 plus 4, 3 is equal to 0. Accepted? 3 is the inverse of 1. Now, what is the inverse of I in the codomain? Minus I. I and minus I inverses to each other. As you know, I dot minus I is equal to 1. So, inverse of I is minus I. Now you have to pair inverse with the inverse. So 3 you should pair with minus I. Now there is only one element left. So you should pair 2 with minus 1. Now what I am writing, define the function f from z4 to z by f of 0 is equal to 1, f of 1 is equal to I, f of 3 is equal to minus I, f of 2 is equal to minus 1. And immediately we mentioned that by defining F like this, F is a homomorphism, F is 1, 1, F is on 2, hence it is an isomorphism. Therefore, the two groups Z4 and G both are isomorphic. That was the conclusion. So whenever a question is given that are these two groups are isomorphic or not, we have to do like this. The fundamental thing is whether both the sets have equal number of elements or not. That is the fundamental observation. If it is so, then you have to build or construct a function in such a way that inverse is mapped with corresponding inverse. Order of A is equal to order of F of A. Following this type of criteria, we should build a homomorphism as well as a bijection. Okay? Any other queries or the methodology for anyone? How it is constructed actually? Tell me. If it is clear, I will take a definition now. Right. Now, the other definition is, as you know, what is meant by an isomorphism. We have one more word called automorphism. So this is nothing but if you take an isomorphism on the set itself. If F from G to G is an isomorphism, then we call it as an automorphism. Now the question is, how many such automorphisms will exist? If so, you put all the functions as a set. We denote with the symbol at G. What is meant by at G? It is nothing but the possible automorphisms from G to G itself. You take all the functions in one set, we call it as automorphisms on G, and it will become a group. The operation is F circle G, the composition of functions. Whenever you take two elements F and G, by taking the composition of functions, it will become a group. So automorphisms on a group is again a group with respect to the composition of mappings. You please take a note of the definition. Then please inform. Now the question comes, is it possible to define an automorphism always? Isn't it? Is it possible to define an automorphism always? Do you have a question or not? Are you getting any lag between my voice as well as video? Tell me. Is it there? Okay, thank you. So, now whenever you have a group G, suppose you fix an element in G, then always define the function FA from G to G such that FA of X is equal to A inverse XA. Now see how the function is defined. In the whole set G, I took an element A. Now the function is defined in such a way that FA from G to G by FA of X is equal to A inverse XA. Whatever the X you take, you are defining the function like this. So this will become an isomorphism. So what is automorphism of the group? So it will consist of isomorphisms which are defined like this. So this type of definition or this type of automorphism, we call it as inner automorphism. We call it as inner automorphism. So apart from taking like this, if you define any other automorphism, that we call it as outer automorphism. So apart from fixing an element, if you define in a different way, that we call it as outer automorphism. Now tell me wherever you have the doubt. This definition you have a doubt? Yes? See, if we define a function like this, for all x belongs to G, you are defining like this. If you have a visualization or picture, you can take like this. So this is G. You are defining a function from G to G, which is FA. I fix an element A. So whatever the x you take, it is paired with A inverse XA. For all x belongs to G. This type of mapping will become an automorphism. Okay? Right. So, apart from fixing an element, if you define in any other way, this type of automorphism, we call it as outer automorphism. Apart from basing an element, if you calculate any other isomorphism, that we call it as outer automorphism. Right? So, at G is nothing but set of all functions, which is a group with respect to the operation composition of functions. And it contains inner automorphisms as well as outer automorphisms. That we need to understand. That's all. Okay? Is it clear to all? Now, at this point, I want to conclude about the homomorphism concept. While going to the next chapters, again we need to do some kind of problems based on this homomorphism as well as automorphism. Right? Now we start the interesting chapter, which is permutation groups. Let us discuss on it. So this is permutation groups. Now the question is, what is meant by a permutation? Suppose you take a set S, you define a function from S to S itself. It is a bijective function. Then this bijection, we are calling it with another name as permutation. So in a short manner, what is meant by permutation? It is nothing but a bijection from the set S to S itself. Where S contains numbers, we call them as symbols. So in a short manner, if you take S is equal to 1, 2, 3, what you are doing? You are just defining a bijective function. We are calling it as permutation. So let us pair the elements in a simple manner. So 1, 2, 3, 1, 2, 3. So you can pair 1 with 1, 2 with 2, 3 with 3. Is it a bijection or not? It is a 1-1 function as well as onto function. All of you agree? So it is a permutation. It is nothing but a permutation on S. Now, How do we represent this symbolically? We simply write that 1, 2, 3. So 1 is paired with 1, 2 is paired with 2, 3 is paired with 3. We write like this. You can do it in the other manner. Say you fix 1, 2, 3. You have the other elements 1, 2, 3. You can pair in a different manner. Say 1 with 1, 2 with 3, 3 with 2. That also you can do, isn't it? Yes or no? So in this manner, we can write it as 1, 2, 3, 1 is paired with 1, 2 is with 3, 3 is with 2. This is also a permutation. So did you get the idea how we are defining a permutation? Yes or no? So if you proceed like this on this set, how many permutations you are going to make? How many permutations you are going to make on this set? There is an interesting question. So if you write them together, let us observe how many permutations we are going to draw on this set 1, 2, 3. So this is one type of permutation, this is one type of permutation. You can write it as 3, 2, 1, 1, 2, 3, 2, 1, 3, 1, 2, 3. So 1, 3, 3, 1, 2. So I can say 3, 1, 2. That we can do. So 1, 2, 3. In what way you can do it is 1, 3, 2 is completed. 1, 2, 3 is completed. 3, 2, 1, 2, 1, 3. 2, 3, 1. Right. So you cannot find more than this. So here the thing is 3 factorial. So if you take a set having 3 symbols, the total permutations you are getting them as 3 factorial. So if you take a set having n symbols, you will get n factorial permutations on the set. Accepted? So if you collect all these permutations as a set, it will become a group with respect to the composition of mappings. They say F circle G. You know how to calculate F circle G, the composition of functions. So using this type of function, the operation, we can say that all these permutations written together will become a group that we are actually calling it as the permutation group. So symbolically we denote that as Sn. So if you take S as a set having n symbols, Sn stands for the permutation group. So total how many permutations will be there? You will get n factorial permutations will be there. So order of Sn is nothing but n factorial. And what is the operation here? You are taking the composition of functions. So this permutation group, we call it as with another name, we call it as symmetric group. So both names are equivalent. We call with the name symmetric group, we call with the name permutation group Sn. Okay? Are you clear? Now, in this permutation, how many symbols are there? 3 symbols, isn't it? So we called it as a permutation of degree 3. So degree of a permutation is nothing but the total number of symbols actually you are using in that permutation. The total number of distinct symbols you are using in that permutation is called degree of the permutation. Now, since always writing like this is a difficult one, you can represent this permutation in a short manner as, for 1 the image is 2, for 2 the image is 3, for 3 again you will get 1. So this is also equivalent. You can write permutation exhaustively like this, or in a simple manner you can write like this. This is also correct. So this permutation we call it as identity permutation, because every symbol is mapped with the same symbol. You are not getting any different one. 1 is with 1, 2 is with 2, 3 is with 3. It is nothing but the identity function. The symbol is mapped with the same one. And here if you want to mention, for 1 the image is 3, for 3 the image is 1, and 2 is paired with 2. So for this thing we will write like this. Okay? Are you clear how we are representing a permutation? One more thing is, as you know, it contains maximum 3 symbols. There is no need to mention these two separately. If I simply write like this, by default I need to understand that the smallest value is 1, the largest value is 3. So 1 is paired with 3, 3 is paired with 1. The remaining symbols are identity. They are paired with everything. 2 is with 2, 4 is with 4, like that. Let me say, if I have written like this, f is equal to 1, 4, 5, 7 is a permutation with degree 7. So what does it mean? F contains maximum 7 symbols. In the 7 symbols, the pairing is done like that. So if you want to write the permutation F, actually you have to write like this. So for 1 it is 4, for 4 it is 5, for 5 it is 7, for 7 it is 1. Did you get the actual meaning of that thing? 1, 4, 5, 7? Say. For 1 image is 4, for 4 image is 5, for 5 image is 7, for 7 again go back to 1. Now remaining values are nothing but identity. So 2 is 2, 3 is 3, 6 is 6. This is the pairing done. Are you clear? Any questions or doubts you can ask. Now another interesting thing is, since the elements are taken in a cyclic order, 1 is with 4, you are doing like this, 1 is with 4, 4 is with 5, 5 is with 7, again 7 is with 1. So this permutation contains a cycle. Now how many elements are there in this cycle? How many elements are there in this cycle? 4. So we say that F has a cycle of length 4 and degree 7. So degree stands for total number of symbols in the permutation, and length stands for the number of elements which are in a cyclic order. Okay? F may contain only one cycle or so many other cycles. So I am saying that in the permutation F, I can find a cycle of length 4 and the degree of the permutation is 7. That is my actual intention here. Okay. Did you get that? Fine. Now let us do some interesting problems. As I know, we all know that the permutations are forming a group. Let me say, I will take a permutation like this. Now here, you give me the images as you wish. So generally, as and when you talk of mathematically, symbols are nothing but numbers. If you talk permutations in a realistic way, the real life applications, it is nothing but they are using the digital keys, electronic digital keys, where you are making the combination of locks. So where each ups and down is nothing but a symbol. There you can make use of that, the permutations. Okay. So since we are dealing with mathematically, we always think about numbers. So if you come to realistic way, you can take the different combinations possibly with different objects. That may be in the electronic media or print media or any other media you can take into consideration. Clear? Fine. Why not? You can include complex numbers also. Because you just want a bijective function from one set to one set, that's all. You can take any type of things. You can use complex numbers also, not only confined to real numbers. All we are just having that, I pick up a set having some numbers. We are calling them technically as symbols. For the same set, you are pairing one value with one value. That's all. That we are simply calling it as a permutation. Fine. Is the concept clear now? Right. Now you give me your images as per our consideration. You give me some input for the images. From 1 to 6, you give a combination to me. All right, 3, 6, 4, 2, 5, 1. Since f is a permutation, suppose you want to take the inverse of f. What is f inverse? So, f inverse is nothing but the reverse thing you are calculating. So, if you want to calculate the image of 1 here, so in the denominator you check where 1 is there. So here 1 is there. What is the upside value? 6. We take 6 here. For 2, here 2 is there. Image of 2 is here 4. For 3, 1. For 4, 3. For 5, 5. For 6, 2. We will write like this. Clear? How this is written? Is everyone clear with this? How we are calculating f inverse? Right. So, as we know, while dealing with the elements in a group, we know that AB whole inverse is equal to B inverse A inverse. So here also, FG whole inverse is equal to G inverse F inverse. That we do. FG whole inverse is equal to G inverse F inverse. Now the question comes, how to find FG? That is the question. Come with us. Now let us find how to do FG. Right? So shall I erase this? Please take a note of that. So you give me G also. You give me G, some input for me. You give some numbers for me. 315264, right? Now let us calculate F circle G or FG. So let us write them together. Now, while calculating this, you have to follow like this. You have to do the things like this. So what are the image of 1, 3? What are the image of 3, 4? So for 1, I need to take 4. Did you get it? How it is written? Again, for 2, it is 1. For 1, it is 3. For 3, it is 5. For 5, again, it is 5. For 4, image is 2. For 2, image is 6. For 5, it is 6. For 6, it is 1. And the thing 2 comes. So this is F circle G. Clear? Right. Now you can calculate G circle F. So you have to move like this. So for 1, 3, 3, 5, 2, 6, 6, 4, 3, 4, 4, 2, 4, 2, 2, 1, 5, 5, 5, 6, and 3. Now are they equal? So here F circle G and G circle F need not be equal. So at this thing we can say that since it is not satisfying the property xy equal to yx, it is not a commutative group. So it is not at all a commutative group. So we can say that it is just a group which is not abelian. Sometimes it will become abelian, but not always. Okay? So it is not a abelian group, it is just a group. Because commutative property not satisfied here. So can I take the other model? Right? As we know, so order of an element you have done with groups. The same thing comes with order of a permutation. So while dealing with order of an element, you know that while raising the powers of A, you will get identity. So here also, while doing the powers for a function, you should get the identity function I. That we need to discuss. So for a small understanding, let us take an example that f is equal to 1, 2, 3, 4. Now you give me some input for it. You give me some input for it. 2, 4, 3, 1, right? Now let us write the powers. I will take the other one also. So I just want to calculate f square first. So if you compare for 1, 2, 2, 4, 2, 4, 4, 1, 3, 3, 3, 3, 4, 1, 1, 2. Again you go for f cube. F square dot f. So 1, 2, 2, 1, 2, 4, 4, 2, 3, 3, 3, 3, and this is 4. This is equal to I. You accepted? Now what is the order of the permutation here? 3. So is everyone clear how to calculate order of a permutation? So this thing you can do with any type of degree. 4 symbols, 5 symbols, 10 symbols, n symbols, whatever the case may be, you can do like this. One interesting thing we can observe here is, suppose you took a permutation having different cycles in it. Now you pick up the maximum cycle length. So order cannot exceed that much maximum cycle length. Let me say, while writing f, I took a big permutation. Here I got a cycle of length 3. Here I got a cycle of length 4. Here I got a cycle of length 2. So among which the maximum thing is 5. So generally order of the permutation will be 5. Okay? Clear for you? In general, order of the permutation will be 5. The maximum value of that cycles. Not always plus means you are adding them up, the values 3 plus 5 plus 2. You are saying that will it come always or occasionally? So I am saying that if you have taken a permutation, it contains a 3 cycle, 5 cycle and 2 cycle, among which what is the maximum cycle length? 5. So if you calculate f power 5, you will get identity. You will get identity. So if not, you take LCM of these numbers, then f power that number is equal to identity. That you can take into consideration. Okay? So generally while calculating the order, that thing we follow. I will give some list of problems to calculate these things. And let us do some problems also. We will discuss, then we can take the part. You take a note of these definitions. You just take a note of these values. After noting, please tell. Now, let us take the problem which gives an idea that this is my permutation F. Now, first of all, let us write that in the form of cycles. So, for 1, it is 3, for 3, it is 4, for 4, it is 7, for 7, it is 5, for 5, it is 6, it is 2, it is 1. This is the cycle. Accepted? Please check the pattern of the images. How I have written. Actually, not only with the starting number 1, you can do that with any number. You can start with 2, you can start with 3, but you are just writing a cycle. That's all. All you are doing is nothing but writing a cycle. You can start with anywhere. Generally, we start with the starting number 1. Okay. Now, this cycle, I am going to represent it as transpositions. So, cycles of length 2, I am going to write. The general pattern is you fix the first number, then take the every one. So since for 2, again you are getting 1, there is no need to write 1 again. So this is the thing, actual cycle you have. 1, 2, 3, 4, 5, 6, 7 symbols actually came. Now we write like this: 1, 2, 1, 6, 1, 5, 1, 7, 1, 4, 1, 3. That we write it actually. Please check on that. How I have written. The actual thing generally we write it as so generally we follow this pattern. So you fix the first element, you take everyone 1, 2, 1, 6, 1, 5, 1, 7, 1, 4, 1, 3. Okay. Please take a note of that, how it is written actually. So did you get the actual meaning of it or not? Now, the actual thing here is here 1, 2 means For 1 it is 2, for 2 it is 1. Remaining are taken as identity. So 1 6 means for 1 it is 6, for 6 it is 1. Remaining are taken as identity. Similarly others. So 1, 2, 3, 4, 5, 6. So if you multiply all of them, this will come again. That is the actual meaning there. Okay? You are simply bifurcating into the small parts. You can cross check that. Is everyone clear? How we have written actually? So if you multiply the entire product, you will get the original thing. That's why I have taken that every permutation can be written as product of transpositions. Every permutation can be written as product of transpositions. Now the question is, in this, how many transpositions are there? How many transpositions are there? One, two, three, four, five, six. Right? What is meant by transposition? A cycle having only two numbers. This is a transposition, this is a transposition, this is a transposition. Are you getting? A cycle of length 2 is called a transposition. So total 1, 2, 3, 4, 5, 6 values are there. Each 6 even number or odd number? So we call it as even permutation. So the given permutation is nothing but an even permutation. Clear? Clear for all? Right. Now let us take some more examples which gives you a total idea. Now you take the permutation as the values are taken as now let us find what are the cycles in it. So for 1 it is 3, for 3 it is 4, for 4 it is 5, for 5 it is 6, 6, 7, again 7 you are getting 1. This is one cycle, right? So if you write like this, the transpositions are nothing but 1, 7, 1, 6, 1, 5, 1, 4, 1, 3. And you can say 2 is nothing but 2 here. So here you have product of 5 transpositions. Therefore, it is an odd permutation. Clear for you? Please take a note of that. Now, if you want to take another example, you take the values as now let us write the cycles here first. For 1 it is 7, for 7 2, 2 3, 3 1. This is one cycle. Okay. So 1 is completed, 7 is completed, 2 is completed, 3 is completed. For the rest you have, for 4 it is 8, for 8 it is 4, close. So 5 5 6 6. Is it clear for you how it is written? The cycles first. Now, this is a transposition. There is no need to simplify this. This is a single element cycle. This is single element cycle. There is no need to modify them. So coming for this, you have 1 3, 1 2, 1 7. You can convert this 4 cycle like this. And this is 4 8. This is the answer. Any questions? So 1, 2, 3, 4. This is not taken into consideration. So product of 4 transpositions. So it is even permutation. So I am not considering them. I am considering cycles of length 2 only. Okay? Clear now? How we are writing actually the product of transpositions, and we are mentioning that as even or odd. Fine. Now let us take some more problems. I think compared to abstract algebra syllabus, this part will be interesting for everyone, for students. The permutation groups part, I hope so. Because there will be some problems which will be interesting for you while solving these kind of things. So please take a note of this problem. Now, here we need to understand that this is a permutation, this is a permutation, this is a permutation, and this is a permutation. So here I have taken 4 permutations which are taken as the product. So if you take the name F, so F is nothing but F1 circle, F2 circle, F3 circle, F4. So the product of these 4 values is nothing but F. So once calculating F, I need to represent F as the disjoint cycles. That is the actual problem given there. So I have given the product of 4 permutations, which is nothing but F. So once finding the product, you have to represent the resultant permutation as product of cycles. Clear? The concept of the problem? Now, if you understand that in each permutation, so what is the degree of the permutation? I mean, because I have taken 4 permutations here, what is the maximum degree for each permutation here? In other words, here 3 doesn't mean that. I am not talking about the cycles. So if I want to write a permutation, I must know what are the total number of symbols used, isn't it? So the total number of symbols used here is 7. Accepted? So each permutation I have to write 7 symbols. So here in the first permutation you should take 1, 2, 3, 4, 5, 6, 7. So here for 1 it is 3, for 3 it is 2, for 2 it is 1. Remaining are taken as identity. So this permutation you have to take it as, so for 5 it is 6, for 6 it is 7, for 7 it is 5. So remaining are nothing but identity. So for the next one also, so for 2 it is 6, for 6 it is 1, for 1 it is 2. And here you have one more thing. There for 4 it is 5, for 5 it is 4. Remaining are identity. So this is nothing but the product of 4 values. Are you getting it? This is F actually. So apart from writing the lengthy expression in a short manner, it was written like that. So did you get the idea? How the actual permutation product is given? Now you need to evaluate the product. It is very simple. So here F is nothing but so you can do in different ways. First, you calculate the product of these two, then you calculate the product of these two, then again you calculate the final product. That you can do. Otherwise, in single step, you can do the product. How it is coming from rightmost corner to the front model. So here, for 1, the image is 1. So for 1, it is 2. For 2, it is 2. For 2, it is 1. So it should take 1 here. Clear? I am checking for the 4 combinations in a single step, so that space will be saved. The paper will not get wasted. Okay? Yes, first you do 2 things. Then you do 2 things. Then you can club them. That also you can do. So if you say it is of the form A, B, C, D, first you do the product of these two, then you take the final result. But while doing, we always do from this way only, not like this. We go for this way. Always we do. So while calculating the product of these two, we calculate from B to A like this. For this also, we calculate the product like this. Here onwards here. Then we take the final product. Okay? Is everyone getting the thing? In a single step we can do. Is this comfortable for you? For understanding? In a single step how we are doing? So here, for 2, the image is 2. For 2, it is 6. For 6, it is 7. For 7, it is 7. So we should take 7 here. Again, for 3. For 3, it is 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 2. We should take 2 here. Right? So as one of our friends replied, this is the answer. 1726435. So is everyone comfortable in getting the answer? Right. Now, you actually calculated what is F value here. So from this, you need to write it as product of cycles. So if you consider that for 1 it is 1, for 2 it is 7, 7, 5, 5, 4, 4, 6, sorry, 6, 3 and 3 it is 2. So this is the cycle. This is nothing but product of cycles there. That is the solution of the problem. Please check. After noting, please tell. Any queries for anybody, or is that clear? Right. Now, we can observe the properties of these permutations. So if you feel that even permutation as plus, odd permutation as minus. Yes, in the previous problem it is nothing but an odd permutation, because you will get 5 transpositions, isn't it? So previous problem, it is an odd permutation. Okay. Right. Now, what happens if I have taken an even permutation and I take odd permutation? If I multiply them together, so what is the resultant one? Is it an even or is it odd? There the question comes for us. So for this, for our understanding, let us take that even permutation with the symbol plus, odd permutation with the symbol minus. So plus into minus gives that minus, so it is odd permutation. So the product of even permutation and odd permutation is nothing but odd. So if you take odd into odd, so you will get even permutation. So you will get the product of even into even. Again it is even. So are you getting? The product of even permutations gives what? The product of odd permutations gives what? The product of even into odd gives what? Fine. Yes or no? Now here some of the results are identity permutation is always taken as even permutation. Identity permutation is always taken as even permutation. So another thing is inverse of odd permutation is nothing but odd. Inverse of even permutation is nothing but even. And a transposition is always odd permutation. You please take a note of them. After noting, please tell. Any questions, any doubts for anybody? Now, another thing is so I have taken a set S with n symbols. So if I consider all the possible permutations on S, it is nothing but the symmetric group. Sn having n factorial permutations. Now the question comes that since you know how to bifurcate that this is even permutation, this is odd permutation, I have taken a set with myself. Now I want to calculate in the total set how many even permutations are there, how many odd permutations are there. Then there is a result that always half of them are even, half of them are odd. So if you take total n factorial permutations, in which half So 1 by 2 n factorial are even permutations and 1 by 2 n factorial are odd permutations. Did you get that? So which we going to discuss as a theorem in the next class. Is it actually true or not? We are going to verify that by means of a theorem. Okay? Are you getting the context? Suppose if I say that S is equal to 5 symbols. So Sn is nothing but 120 permutations. So among these 60 are even, 60 are odd. Did you get it now? The actual content, everyone. Right. So if you consider all the even permutations into one set, if you take all the even permutations into one set, it will become a subgroup. We call it as alternating group. We denote with the symbol AN. So what AN stands for? In the whole permutations, you separate all the even permutations into one set. That you write it as a separate set. It will become a subgroup for Sn. We call it as alternating group and denote with the symbol AN. And one interesting observation here is, it is not only a subgroup, it is normal subgroup of Sn. The set of all even permutations will become a normal subgroup of Sn, which we call it as alternating group and denote with the symbol An. And we prove the result theoretically in the next class also. So is it really a group or not? Is it a subgroup? Is it a normal subgroup or not? That we can verify it physically. Okay? Are you getting this? The content what I am saying? Now, at this point, I want to close our today's discussion. Tomorrow we will take some result-oriented concepts over these permutation groups. And before that, I just want to convey advanced Happy New Year to everyone, so you can enjoy the day for today. Tomorrow we have the class as usual, so we will discuss on permutation groups again. So I wish everyone advanced Happy New Year. Thank you very much for your cooperation. So if you want to add something, you can add. And tomorrow we have the same session. There is no difference in the timings, we take as it is. So do you have any objection for taking like that? For taking class tomorrow? Right, then done. So that's all for today. We will meet tomorrow then, in the new year.